Okay. Thank you so much. And thank you so much for coming here. Have you enjoyed the exhibition upstairs? Isn't it awesome? I mean, the artists have done a phenomenal job. Art is about communication. Art can tell a story. Art can move you in many ways. There's many types of art. We're going to dig into that a little bit today. Some of the art which is upstairs about meteorology. The exhibition is called Cumulus. Let's see, let me get to that. That's it, The Art of Meteorology, Cumulus. And it's a great exhibition. I'm very excited to be a part of it. We have several of the artists actually here. How many of you are artists in the exhibition? I'm just curious. We got a couple, 1, 2, 3, 4, we got a couple of them. Well, you might see your own work here in the talk, because I'm just going to do a little bit of a deep dive into meteorology as it relates to some of the pieces of art exhibited upstairs. So we're going to go a number of places. We're going to talk about the monsoon. We're going to talk about light and scattering of light and how that plays into the coloration of the atmosphere. We're going to talk about thunderstorm formation. We might talk a little bit about lightning. Anyway, we're going to have a lot of fun. And if you ever have a question at any time, just raise your hand. This is a small group. It's a great group. And we can have a conversation about what we are seeing today. So the Cumulus exhibition, just to read the title of it, it explores the processes and phenomena of the atmosphere through art. It coincides, of course, with the Southwest or the North American monsoon, which just kind of came to an end here. Now it's been clear and hot again. It's an iconic seasonal pattern here, and we're going to talk a little bit about the monsoon as well. Anyway, I want to get started talking about some rather famous historic art that is extremely atmospheric, that has a lot of weather. This is a great piece, J.M.W. Turner, 1842. It's called Snowstorm, Steamboat Off a Harbor's Mouth. And you can almost feel this art, can't you? Because of the atmosphere which is engendered here. The ocean and the sky almost meld together. There's actually very little difference between the two, but the techniques used by the artist can bring out that difference. You see light coming through in the middle, but you almost don't know if that's like the sails of the boat or if there's light coming in, being reflected or refracted into the scene through the snow. You almost don't know if it's daytime or nighttime. What is the visual language being spoken here? How does it make you feel? What do you hear when you see this art? What do you see? This is what art does. And there's a scientific process behind everything we're looking at. This is beautiful stuff. Completely different. Georgia O'Keeffe, Sunrise, 1916. A simplistic watercolor, a beautiful color palette here, but it makes you feel completely different, doesn't it? It's a complete circle. It uses fresh colors. It's almost like the start of a new day. It's a beautiful sunrise that has a very different feeling from the last piece of art. Okay, let's talk about the east wind. The east wind, almost a haunting interpretation of weather here. Can everybody hear me okay? I just want to verify. Almost a haunting interpretation here, where we have the rain, almost black, almost like daggers coming into this, well, phantom-like house or tree above the house. There was certainly a negative impression involved with the weather in this piece. Note the color of it. It's not a pretty color. And then a lot of you might be familiar with Ed Mel's work. He does beautiful, beautiful works, a lot of it in the Grand Canyon. And if you've ever seen a sunset at the Grand Canyon, doesn't this kind of capture it? You have the color, you have the fleeting showers, you have the aged rocks being impacted by like the passing monsoon storms. An indelible image, which just, to me, really captured the essence of what the Grand Canyon is during the monsoon at sunset. I've this year had the chance to see a couple beautiful sunsets at the Grand Canyon, and I wish that my memory was as good as what was captured here. But anyway, we're talking about the art of meteorology, and that's what's being captured upstairs. And what I'm going to be talking about is the science behind the art, okay? And as I started to tackle this, it discovered that this is pretty difficult. This is not very easy because an artist takes, let's say, a landscape, a storm, a physical process, let's say a rowdy ocean, during a snowstorm, and then brings emotion, brings interpretation, brings additional elements to it. And I'm here to kind of go the other way, to look at the processes that might have been behind what was seen in that art. It was a bit of a challenge, but I think we're going to have a lot of fun with this today. So let's get started with the basics. This show is kind of centered around the monsoon. It's monsoon season. So let's talk about, well, how does the North American monsoon come about? How does the Americas get their own monsoon? It's actually a fascinating season. It's my favorite season here in Flagstaff for sure. I love the lack of wind normally. I love the beautiful skies. I love the storms, and the power of the storms I find very moving. Let's talk about the North American monsoon. This is a typical 500 millibar weather chart. It's kind of meaningless to 90% of you, but basically you can see the arrows blowing from the southwest to the northeast over Arizona. Typical late spring conditions over the area, which brings dry air over the desert southwest. We all know that April and May and most of June is very dry because the predominant weather pattern is this. But the heating of the Four Corners, the arid terrain, tends to form a thermal low, which tends to draw moisture into the area as the season progresses, as the heat progresses and builds through the late spring and into the summer. You may have heard, or you might be aware of, that there is kind of a correlation between dry winters and wetter monsoons, or wet winters and a late onset of the monsoon. We saw that back in 2023, when we had the very big, heavy winter, and really the monsoon circulation didn't get started until late July. It was a late onset. And that's because of the formation of this thermal low, which needs heat, which needs a lot of radiation from the terrain, from the dry terrain, to really form. And what that helps to engender is high pressure near the Four Corners. So the high pressure, which is typically down in Mexico, kind of moves to the north in a broad scale sense, and now brings in rich moisture from Baja, from the Gulf of Mexico, from the Occidental in northern Mexico. And that's what brings the moisture that helps form the thunderstorms we see every monsoon. Now, thunderstorms are exciting to me. The power and the beauty of their development is exceptional. Monsoon thunderstorms and all thunderstorms are formed in what's called an unstable atmosphere. That is, simply put, the air aloft is much colder than the air near the surface. So cold that if you took and captured like a parcel of the air near the surface and then displaced it upwards, it would find itself in a surrounding which there's cold air on both sides. So it's going to continue to rise like a hot air balloon. That's why the thermals that are in this time lapse were so violently going up. They're in a very unstable environment. Cool facts about thunderstorm updrafts. They can be extraordinarily strong. How strong? Let me just see some hands. Do you think like an updraft of a thunderstorm can be? That air which is rushing up. Those were time lapses that were sped up about 50 times. But how fast do you think the air can be going straight up in a thunderstorm? Any guesses? Thousands of feet per minute. Okay. 100 miles an hour. Anybody else? That's right. Or enough to loft a grapefruit-sized stone of hail. Think about what the fall speed is of a piece of hail this big. oh, maybe about 160 miles an hour. That's how strong the updraft has to be in a thunderstorm to build it to that size before it falls. A lot of power, a lot of energy in these storms is being released, and that energy can be released in a lot of ways. I don't have time to get into all that, but come to a future talk and we'll kind of get into it. But here you see several stages of thunderstorms building over various parts of northern Arizona. From the National Weather Service on the upper left are some cumulus congestus. Notice that in a typical fashion that the cumulus clouds are flat on the bottom and cumuliform on the top. Anybody know why? See, I love asking these questions because it's like you look at it every day. It's like, well, why is that? You know, what we have is moist air near the surface, which is being lofted and raised, which is rising up. As that moist air rises, it cools. As it cools, the relative humidity rises. When the relative humidity hits 100%, cloud droplets form, and that's the base of those clouds. So you can see that it's water vapor, water vapor, water vapor, and then cloud droplets instantly as it goes up. Fun stuff. Fun stuff. Those updrafts just can't continue going up forever. They eventually do hit a stable layer high in the sky. Could be the stratosphere, could be 60,000 feet in the atmosphere, where finally the atmosphere is warming faster than those parcels are warming as they rise. And you see that most thunderstorms are flat up on top. They have those anvils. They've hit a barrier up high and are now spreading out on both sides. But we're here to talk about some of the beautiful art out there. And something really cool happens when the sun starts to set. And that is the scattering of light changes everything. And our monsoon skies get very, very colorful. And we have some great pieces of art out there that show this. Ruan Miller has a beautiful piece called On Fire, Clouds Bejeweled at Sunset. What I love about this piece is it really captures the color and the feeling of what's going on, the monsoon storm at sunset. Perhaps we see the outline of the San Francisco peaks there. We can see the rain falling down. Notice the cool technique, how the raindrops or the streaks of the rain perhaps are large on the outside and then small in the middle. It kind of draws your eye into some depth right there. The colors match what we see during a monsoon sunset, those oranges and the blues. And, you feel action in this piece, but you feel, I don't know, I feel at peace in this because I hear rain, I hear kind of that pitter patter of the rain. I can almost smell the sagebrush when it rains in this area, in this piece. Very beautiful. And then Karen Bopp has a beautiful piece in the gallery called August Monsoon. Again, capturing so many of the colors that are characteristic of the monsoon over the Southwest. We have the blues, we have some reflection of what looks like the desert in the colors near the ground. Unsure if that's an impression of a lightning strike which is coming down. But the colors are there, and then the form is very representational of the Southwest. Again, a great capturing of the feeling of the Southwest monsoon. So that raises a question: what causes and what processes are in place to create the colors that we see in the atmosphere? Why are the clouds white? Why is the sky blue? A classic question, a classic question. I have a fun story about that. Okay, I'll tell it now. On my PhD defense, great question. It wasn't why is the sky blue? It's why isn't the sky purple or violet, more specifically. And I had to think about that one. I had to think about it. It was an oral exam, so I'm pacing like I do. And I said, You guys got me on that one. You guys got me. And they said it's a trick question, and I'll get into the answer of it here pretty soon. So, why is the sky blue? Why are the clouds white? It all comes down to the process of scattering. That is the light waves from the sun and how they interact with the particles in the sky and the particles of the clouds, the cloud droplets. The atmospheric constituents are very small, okay? The vapor, the chemical constituents in the atmosphere are very small. And when the light from the sun scatters from very small particles, it scatters preferentially different wavelengths. Shorter wavelengths are scattered more than the longer wavelengths. The shorter wavelengths are the cool colors, the blues, the violets. The longer wavelengths are not scattered as efficiently, the reds, the oranges. Hence, why when we look at the sky, we see all of those short wavelengths of light that are scattered in all directions. The sky is blue because the blue light is scattered more than the yellows, the oranges. We see the blue. But violet is an even shorter wavelength than blue. So why don't we see violet? Why aren't our skies violet? Come on, help me out. Ah, that's good. Who said we can't see it? That's right. It's a biological answer. It's not a physical one. It's biologic. Our eyes are not sensitive to those very short wavelengths. I totally missed that one, but I still graduated, so they pushed me through. It's there, absolutely. If we had differently sensitive eyes, yes, we would see the sky and see all of, the Earth very differently. Why are the clouds white? They scatter everything. That's right. We're talking now much larger particles, a different type of scattering, which scatters all wavelengths of light equally. And if you combine all of the wavelengths of light, what color do you get? White. Clouds are white because of that. But, what are we seeing here? Something magical happens around sunset. And that is as the sun gets lower and lower in the sky. And if you can still see it, especially as it's right above the horizon, what color is it often? It's red, it's orange, it's deep yellow. All of the blue light is scattered away from it, and we see the red light, which is left over. And then that red light can then do magic with anything it shines on, whether it be a cloud, whether it be a butte, a lake, whatever it is, it causes beautiful things to happen. And so many of us, photographers, artists love to take advantage of that light. But the light during the daytime is also gorgeous. Gwendolyn Waring has a beautiful piece here, which just captures, kind of a midday, maybe mid-afternoon sky of the blue skies, the white clouds, and the oranges and the greens, or the, kind of the pale greens that are so characteristic of our monsoon season here in the desert Southwest. Vivian has a beautiful piece here, which shows, some rain falling out of a cloud over the desert landscape. But here, I can't help but see physical processes at work in this photograph. You can see rain or some precipitation falling from the clouds. And in places, it looks like, well, it's not quite getting to the surface. It's kind of evaporating, perhaps, before it reaches the ground. This is something we see a lot of here in Arizona, and it's called virga, okay? It's when some hydrometeors, I'm going to use the general term because it could be snow, it could be ice crystals, it could be rain, but it evaporates before it reaches the ground. It can happen, from some dissipating thunderstorms like here on the left, on the bottom right. It can even happen from mid or high level clouds where the ice crystals are falling out and being swept away and evaporating before they hit the ground. But it's not always evaporation which is going on here. Actually, sometimes It's a phase change, which is causing the difference in opacity of the particles that are falling from the cloud. For instance, I would have to know the temperature of the atmosphere to tell you if these aren't ice crystals falling from the sky, which are then turning and melting into water droplets, have a much higher fall velocity, the opacity goes way down, and all of a sudden they kind of become invisible. So it could be melting ice hydrometeors, or it could be evaporating rain. Either one, it could be. Most of the time, it's the evaporation portion, what we see. But it's fascinating. What's really neat to see is to put these kind of clouds into a time lapse and just see all the moisture pouring out of the cloud and then just disappearing and disappearing. It's fun to watch. It's fun to watch. I love this kind of stuff. The atmosphere is a fluid, and nothing really brings that home more than to do a time lapse of some clouds. This happened to be a beautiful inversion event over the Grand Canyon about a decade ago, where the Grand Canyon was full of clouds. And you can just see in this time lapse how, oh my gosh, it just looks like waves in the ocean, doesn't it? The atmosphere is beautifully fluid, beautifully fluid. But what we're seeing here is really interesting. Actually, the Grand Canyon was not full of clouds. Those clouds are probably only a couple 100 feet thick, okay? They're at the barrier between the, let's see if we can get this to play again. There we go. They're at the barrier between the very cold air, which is in the Grand Canyon at this time, which was below freezing. I'm estimating 28, 29 degrees. And the warm air aloft, which was, if you went, a couple 100 feet above the ground here on the rim, was in the low 50s. Okay, so there's a big temperature discontinuity. And the clouds are forming at that discontinuity, where the warmer, moist air is being condensed into the clouds that you're seeing here at the interface of those two air masses. Now, some fun things are going on here. I mean, we could talk about this for a long time. If you happen to be here that day, David, Jeremy, Tom, were either of you at the Grand Canyon during this event? What were the trees like on the side of the Grand Canyon? Covered with rime ice in places. Covered with rime ice. As this supercooled water droplets moved up, higher than the rim, and then moved down. Sometimes they moved up. They were coating the trees in this supercooled, in ice, basically. Because water droplets, a common, often happens, is that the water droplets don't freeze at 32 degrees. Because of the shape and their size, they can actually become highly supercooled. I mean, they can stay in a liquid form to minus 10, minus 15 degrees Celsius, minus 20 degrees Celsius, and they're still liquid water drops. But once they hit something, they instantly turn into ice. That's why on those really cold, foggy winter mornings around here, sometimes there's ice on everything, but yet nothing fell from the sky. It's just those little supercooled fog droplets hitting everything. But did you see how the level of the clouds were rising as the evening was going on and as the sun was setting? I'm still trying to figure that one out. I'm trying to think, well, it's cooling, so the temperature discontinuity between the two air masses is decreasing, so is that why it's rising? I don't know, I still haven't figured that one out. I will one of these days, because you can throw equations at everything and pretty much figure it out if you're smart enough. So we're actually going to see some equations in this talk. Are you guys getting excited? Yes. How did we know it was going to happen? In this case, it was already happening, and it's like we saw it developing. This is actually a fascinating case study because it started about 3 days before, and David can help me out here, as an inversion over the Little Colorado River Valley. And we had stagnant cold air, a lot of moisture on the rim, the Mogollon Rim, that was just melting snow and feeding this cold moisture down into the, what we call the Little Colorado River Valley to the east of us. And as the volume of cold air was just increasing, you could see it in the cloud cover near Winslow and near Cameron, just getting deeper and deeper. And then it started to spill over into the Grand Canyon. And then it was like, oh, this could be real cool. So I'm just kind of driving my car up there before the sun rises and spent 2.5 days up there. Well, as much as I could. I do have a job, so it was spectacular. And then it lasted for, I think, 2 days. So it just lasted for such a long time because we had a large dome of high pressure above us, so very warm air loft, kept the cold air in place, and it just lasted. It was spectacular. Okay, so I see you begging for equations here. Yes. That time lapse was about 30 minutes. Yeah. Okay, this happened the morning before. Okay, where we're seeing the clouds pulsing back and forth. It's almost sunrise, and back and forth. This is over an hour, this time lapse. Well, what is going on here? If you measure the frequency that it's going up and down, it's about every 17 minutes. It goes through 4 cycles, maybe 5 cycles in this video. One of my theories is it's sloshing back and forth from the north rim to the south rim, almost like water in a bathtub. So I said, okay, how can we think if that's even a reasonable hypothesis? Or is that just some harebrained idea from a meteorologist that's been working too long? I don't know, but it's fun to think about these things. That's what came to my mind. So I said, well, let's throw some equations at this and see what happens. So, how come what? That's a good question. I don't know. Maybe there wasn't enough wind. It was very still when that was happening. Very still. And what's funny is when I was there, I didn't sense it was happening. I just, saw it changing and changing again. And I'm so busy, I'm taking pictures. I was there with Derek that day and that morning. And, you're just busy taking pictures. And it's like so cool. But I happened to have this time lapse going in the background. And when I looked at it, it's like, wow, something very physical is going on here. So, of course, everybody here, probably half of you recognize this equation as the gravity wave formula. We saw it in grad school, one of our good friends. If we throw some assumptions at it, like the width of the Grand Canyon, about 9 miles, depth about 3,000 feet, which really does not matter in this equation, as it turns out. Temperature of the cold air, somewhat below freezing, 29. Temperature of the warm air above, about 54. If you look at a radio sounding, you can see that there's temperatures in the mid-50s aloft. If we throw all those assumptions in, you actually get a frequency of about 18 minutes. If the atmosphere was sloshing back and forth, it would have a period of about 18 minutes, which matches and correlates pretty well to the observations. It could be luck. It could just be coincidence. I'm not a fluid dynamicist by any means, but it's kind of cool to throw science at art and see if you can explain some of the things that you see. 2013, December 1st, 6 a.m. So this show is a number of things. The art of meteorology, cumulus, as it's called. It's a celebration of weather. I love this piece, by the way. Doesn't this just bring out the joy of the weather here, of what Andrea has done? It's an exploration of cultures. So much of the tradition of the Southwest art is a very cultural tradition as well. It's an expression of our homeland. It's what maybe we can say, yeah, this kind of defines what my home is. It might be science, which is captured in a moment. And that little vision that you saw at one point, it's like captured. It's like, oh, that is so cool. It's really all of those. It's art, folks. We have some great art up there in the gallery. I need to spend more time with the art which is up there. It's really beautiful. The artists have done a great job. The Center for the Arts here really put together a great vision in bringing this show together. It's beautiful to see. I'm really happy I can be a part of it. And thank you for your time this evening. I'm going to wrap up my talk right here. And we have about 5 minutes for questions before we set up for the next talk. So any questions?